share the
I have
screen
tried to
because
share my screen.
yeah,
Is it
it's
visible?
so we can see your screen.
And is it full screen?
Yeah.
Yeah,
Okay.
yeah.
So let me quickly introduce our next speaker. Our next speaker is Dr. Siddhartha Mukherjee. So Siddharth is currently a postdoctoral researcher at the International Center for Theoretical Sciences in Bangalore. He's working on problems in active and inertial turbulence. He obtained his PhD and MSc in chemical and mechanical engineering from TU Delft in the Netherlands, and he had obtained his BTech in mechanical engineering from the VIT fellow. So today he will tell us about transition to universality and Lagrangian anomalies in active turbulence. Over to you, Siddharth.
All right. Thanks a lot for the introduction and for the invitation to speak here. It's really a pleasure. Um, so I'll just start off. Active matter, basically, active matter is any matter that is animated at the size of individual particles. So you can have living agents, and I use the word living sort of loosely. What these agents typically do is they have an orientation and they propel along the direction where they're pointing. Now, when you have a large number of these kind of agents together, that can give rise to complex flows, and this is a sort of an emergent phenomena. And interestingly, it's observed across nature. So you really see it from the large scale of birds and fish, all the way down to microscopic particles and microtubules and so on. So for this talk, actually, I'll speak about bacteria in particular. So I want to start by showing you this movie here. This is a movie we made recently. It's E. coli cells. So E. coli is typically this rod-like bacteria, and it has all these flagella which pushes them. And when they are in a dilute suspension, like the one you see on the left, they typically do this run and tumble motion. So they move along a certain direction, and then they suddenly tumble and they move in another direction. And for this particular case, their velocity turned out to be roughly 10 micrometers per second. Why I mentioned that is because something very interesting happens when we concentrate this suspension now. So we take the same suspension, we centrifuge it, and then we have a very high density of bacteria. And then they do something very fantastic, which you see here. Um, so it's the same cells again. It's just that their concentration has increased a lot. And the movie on the left is just a larger viewing window, and then it's zoom in on the right. And you see the flow is highly chaotic. It's very irregular. And the velocities have really shot up. So it's moving now around 50 at 50 micrometers per second. And this begins to resemble what we actually call turbulence, uh, which we see, from the atmosphere to any daily applications. This is now happening at the micro scale. So it's very interesting that this sort of a flow can show up there. Now, regular turbulence we know is described by the Navier-Stokes equations. So then can we also have an equation that describes these kind of fluids? So I'll be talking about the modeling aspect of this problem. Yes, it turns out there is an equation which was proposed in this paper by Wensink, where they studied bacteria. And it's a generalized hydrodynamics equation. It's a little different from the Navier-Stokes, so I just want to point out a few differences. The first thing is that you have a generalized nonlinearity. So it appears with a lambda coefficient. Sorry. You have your regular diffusion term comes with a negative sign here, but that's compensated by a higher order Laplacian. So these two terms together, they give rise to pattern formation in Fourier space. And in the end, you have a toner 2 driving term, which has that alpha and beta u squared term multiplied by u. The main thing is that alpha, when it's positive, it behaves like friction. When it's negative, it injects energy into the system. So for this study and generally, we've mapped all these parameters to the experiments, what was proposed for the experimental system. The only thing that will vary for this talk is alpha, where we inject sometimes more energy, sometimes less. And if you simulate this equation on a periodic domain, you see the movie which is in the center, which shows you the vorticity field for this bacterial turbulence on the left. And here you really see these counter-rotating vortices moving around. And to this, we add Lagrangian tracers, which are simply particles that follow the flow. And I've just shown you a few trajectories that emerge for different levels of activity. So this is the system that we have now. And it's nice that we can simulate turbulence in active suspensions. But then the question arises, what is really turbulence here? Is this really turbulent? So for that, we really need some features of turbulence that are quantifiable and very concrete as well. It's not just a visual semblance. So we'll focus on these four features of turbulence, namely universality, which is that the energy spectrum scales universally in 3D turbulence. Now, it doesn't matter how you're driving the turbulence, whether it's in a closed region with walls in the atmospheric boundary layer. The energy spectrum has a universal scaling, which is minus 5/3. A very important property is intermittency, which means that any quantity like a gradient, let's say over space or acceleration, these kind of things are highly non-Gaussian. So as the Reynolds number goes up, these distributions become more and more non-Gaussian. What does that mean? That means that typically you'll have a flat signal with very low amplitude, but suddenly there'll be a burst and you'll have a very high amplitude locally, both in space and time. Turbulence is highly chaotic. In fact, if you measure chaos in, let's say, simulations of 3D turbulence, it turns out that the level of chaos, which I represent by lambda here, I'll explain what it means later, that more or less increases in an unbounded fashion. And lastly, turbulence is also highly diffusive. So if you just look at tracers in inertial turbulence, they have a mean square displacement with transitions from ballistic to diffusive. So ballistic is t squared scaling, and then it immediately falls to diffusion, which is t. So what happens to all of these in active turbulence? So let's first look at the energy spectrum. But before that, I want to show you just visually what happens to the flow. And also, I want to point out that these numbers that we are using here for alpha, they are not necessarily very important. The main thing you need to know is that we have mildly active turbulence on the left, which is alpha, let's say around -1. And you have highly active turbulence where alpha is much lower than -1, let's say -6 or 7, something like that. So I'll use these terms in a slightly hand wavy fashion, but I hope it conveys what I want to show you. So let's look at the energy spectrum. So on the first panel, you see the energy over wave number k. Now, for mildly active turbulence, which is the panel in the middle, you generally have one vortex scale. And it's sort of a distribution of the same sized vortices everywhere. So the energy spectrum, of course, then just rises up to that characteristic length scale, and then it falls off. Now, when you start increasing the activity, the slope of the energy spectrum starts reducing a little bit. In fact, when you go to highly active turbulence, it changes sign. So it goes from being a positive slope to a negative slope. Now, what does that mean? Well, once you have a negative slope of the energy spectrum, that means all the scales are energized, from the small scales to the large scales. And more importantly, the larger scales, in fact, have more energy than the smaller scales. So there's sort of an inverse flux of energy as well that's happening in this system. So we can fit a power law to the smaller part of, well, to the lower wave number part of the energy spectrum and extract the exponent delta. And this is what I show you here. So this is delta, which is the spectral exponent over different levels of activity. And now you clearly see that there's a transition. For high levels of alpha, which is, let's say, more than -4, the slopes, they linearly decrease with activity. And then there's sort of a phase transition, and the delta value, it reaches a constant, a universal constant, which is turns out to be -3 halves here. And it's quite interesting that the number, in fact, turned out to be -3 half, because the same exponent is also seen in, let's say, MHD turbulence as well as wave turbulence of some kinds. So it would be interesting if actually active turbulence ends up being closer in universality to some of these kinds of flows. So that's something to look into. So clearly there's a transition here. Now what happens to intermittency? Let's look at that. So I just first want to describe the quantity we measure for intermittency, which is very simply the velocity difference. So that's the quantity on the top right. I don't know if you can see my cursor. It's on the top right there. It's simply the velocity at u at x plus r minus velocity at x, and you project this difference along r. So what you get is this delta r of u, and typically you do this in an isotropic manner. So you average it out over all orientations of the r vector, but you want to bin this sort of information over different values of r. So if I just pick one value of r and I look at this distribution, then I get these PDFs which I've shown there. And the arrows there are pointing to increasing level of activity. So you see that, and there's a dashed line which sort of shows you a Gaussian distribution. So you see that you're becoming more and more non-Gaussian as alpha increases. And this you can quantify just by looking at the kurtosis of this distribution, which is nothing but a measure for non-Gaussianity. So if your distribution is Gaussian, then you have a kappa value of 3. And if it's non-Gaussian, it's going to be higher or lower. And here what you see is that, again, this alpha C, sort of a critical activity shows up, to the right of which everything is Gaussian, and to the left of which things start becoming non-Gaussian. So just to summarize this slide, we clearly see that there is a critical level of activity beyond which we have universality in the energy spectrum scaling, and we have intermittency. So then we move on to the next item, which is
Siddharth, may I just
yeah,
ask a
yeah,
quick question?
yes,
So in
please.
your previous slide,
Yeah, yeah.
when you define the velocity difference thing, is it really a ceiling function, or because the image has overlapped on the right, so it's actually just a difference?
Say that again. What's the ceiling function?
It, so your definition of delta RU, it looks like a difference and the ceiling function, but I think it's not, right?
No,
It's just a
it's
square bracket.
yeah, it's just a square bracket. Sorry, and it's multiplied by the
Okay,
unit
so I
vector
think
r. Yeah, yeah.
okay, I think if the picture overlaid on the text, so it looks like a
Oh,
ceiling
yeah, yeah,
function.
yeah. No, no, sorry, sorry.
Yeah,
Yeah,
sorry. Go ahead.
yeah, yeah. So next thing we look at is chaos. I mean, after the last talk, I don't need to describe much what chaos is. But let's say you have two nearby trajectories in a chaotic system. They are going to diverge. That's the key idea. And I've given you a brief example from this Lorentz model, which is a very classic example. So you have a blue and a pink trajectory. They both evolve on the attractor, this butterfly attractor, but they stay close together only for a short time and then they become uncorrelated. And if you measure the difference between them and you plot it out over time, you you typically get an exponential growth phase with a lambda t, and then it saturates. And this lambda is called the Lyapunov exponent. So that gives you a measure for the degree of chaos. So this is exactly the game we are going to play with active turbulence. Now, what you need to do there is let your simulations evolve up to a steady state. So you have a well-defined, well-developed flow. So let's say you take one set of parameters, you get the flow, you make a copy of that simulation. So you get a twin, and you perturb the twin with a delta x, some perturbation. And you're free to choose how you want to perturb. You can do it with white noise or all over space. Um, what you then want to measure is the difference fields. So you subtract these two now, and you measure how delta U and delta omega, which is the vorticity, the difference vorticity, how do they evolve over time? And you can also define a decorrelator, which is just the sort of energy equivalent of the delta U field. So before showing you how this proceeds, I want to give you a visual impression of how the perturbation grows, because it's very beautiful that you can start with a localized, this is really the butterfly effect that you know of. So we start with a very tiny perturbation, that circle that you see in the first figure. So it's for mildly and highly active turbulence. And as we move to the right, we have different time instances, and you see that the perturbation really just grows out. Interestingly, for the mildly active case, it happens in a more or less isotropic manner, whereas the highly active case also has a lot of advection. So it sort of redistributes there in a more nuanced way. And finally, they reach saturation, and it looks like a vorticity field in itself. So from this, we can now look at the decorrelators, which I've shown here, for different levels of activity. Now, clearly, you see that there is that exponential growth regime, which I was telling you about, and then there is saturation. So we can fit a line to that exponential growth, we can get the lambda. And the inset shows you the Lyapunov exponent as a function of alpha. So here again, something very interesting happens. Of course, as you increase the activity, the Lyapunov exponent increases as well. But again, there seems to be some critical alpha beyond which lambda sort of saturates. And that shows that there is, in fact, a maximally chaotic state in these suspensions. And that's quite interesting. Why? Because this does not happen in inertial turbulence. So there, if you increase the Reynolds number or so, you will keep having higher and higher Lyapunov exponents. But here, because we also have a finite range of scales, because of the way the flow is forced and organized, it's happening from the small scales all the way up to the large scales. You do not have access in arbitrarily increasing the range of scales, and that sort of reflects here. Another very interesting thing you can look at is the spectral growth of the perturbation. So here, let's just focus on the middle panel first. So the different curves are at different times. This is just the energy spectrum of the difference velocity field now. And the diagonal line that you're seeing at the bottom, that's the initial perturbation. So here you see that immediately it picks up a self-similar shape, the energy spectrum, and it sort of grows in an equidistant manner until saturation. That's what's happening. So it's not too interesting. But for the highly active case, something much more rich happens. So now let's look at the third panel. So again, you have that straight line. There's a self-similar shape and it starts increasing. But I've labeled these things as first, second, third. That's just to show you how the perturbation is saturating. So first, the smallest scale saturate. And only after the smallest one is saturated, then a slightly larger scale will saturate as the second one. Then even a larger scale than that, that's the third, and so on. So this black arrow is just pointing in the direction of when which scale sort of vaguely saturates. And this is really interesting that the largest scales that you see, which is the smallest wave numbers, they are the slowest to saturate, in fact, in this case. And this sort of reflects what is known also as the permanence of large eddies in turbulence. So this schematic is showing you that you can have a scale dependent Lyapunov exponent as well, and the largest scales are slowest to saturate. And this is exactly what was predicted for inertial turbulence. So it's interesting that while there is maximal chaos, this sort of a phenomena still shows up in active turbulence. So this is the picture from the Eulerian perspective. Now we ask what happens to the Lagrangian picture beyond this critical level of activity. So let me just start off by showing this comparison where we introduce a puff of tracers into the flow. So you again have mildly and highly active turbulence, and I've colored them yellow and blue just to sort of represent mixing. And I want you to notice the differences between the left and right, because there are some very clear differences in dynamics. The main thing on the right to note is that you have these sort of material lines or segments that stay close by. So they retain their shape and form, and then they are just translated along for a certain time, and then they twist and they break apart. This does not happen on the left. So by which I mean that on the right hand side for highly active turbulence, there's a mixture of sort of diffusive motion and persistent motion. And this clearly shows that there is a change in the Lagrangian dynamics, which will show up once we calculate the statistics. So we can quantify that, for instance, by looking at mean square displacements of tracers. So here I've calculated this mean square displacement, which is simply just how far does a tracer diffuse from its initial position. You average it over all tracers, and I've done that for different levels of activity. So you see that for the frictional values of activity or mild levels of activity, you get that classic ballistic to diffusive transition. So delta x square, it goes first as t square, then it immediately falls to t. But then again, for the highest level of activity here, which is beyond that alpha critical, which I was talking about, you see a very robust regime of superdiffusion. This is almost over 2 decades in time that delta x square goes as t to the 4/3. And that's very exciting because this was something that was not seen in simulations of active turbulence before, but it's very important. Why? It's because of this one paper that came out some time ago, which showed that bacterial swarming can actually have Levy walks. And Levy walks are a special kind of a trajectory where a particle wants to be persistent for a certain time. So it picks a direction, it keeps moving, and then it suddenly changes its direction. So it waits between the times when it wants to turn. And it's a very particular form of that waiting time which leads to Levy walks. So we wanted to measure, do we really see Levy walks in these simulations? So for that, we need to do statistics on trajectories. So here you see one sample trajectory, which I've broken into segments. The segments are just picked out by picking a turning angle threshold. So you say, if my particle changes direction beyond a certain angle at a point, that's a turning point. And then you have basically different segments. And now you can measure both the distance and the time a particle spends before it turns. And then you look at the distribution of those times over all the particles that you have. And this distribution also turns out to be a power law. And within our numerical errors, it's pretty close to, gives an exponent very close to -8/3. Now, and as you see that this distribution is sort of robust for several choices of this turning angle threshold, because it should not matter too much upon what you're defining as a turn, but the statistics should be sort of built in into the trajectory. And this is robust. So most importantly, the 4/3 from the anomalous diffusion and the 8/3, they together satisfy a constraint from Levy-Walk theory. So we can confidently say that, yes, the anomalous diffusion is coming from Levy-Walks. So I don't have much time to go into the details of a lot of other Lagrangian anomalies that arise because, see, you can imagine once there are Levy-Walks or some sort of super diffusion in the system, any Lagrangian measurement you make is going to be affected by it. So we found that happening for first passage times. We found it for pair dispersion statistics. But what I want to talk about very briefly is this very interesting feature called dynamical heterogeneity, which we found in the flow. Now, what does that mean? That means that the fate of a trajectory is really determined by where it starts in the flow. Well, if you measure it over a long enough time, then it's the same trajectory, different parts of the same trajectory. But let's say if you start in these spotted regions, which are shown on the right, you get these blue kind of trajectories, which are very diffusive and they're mixing around. But if you start in these streak-like regions, which is on the right, these are sort of banded vorticity structures. I want to point out that these don't have anything to do with the streaks you see in, let's say, channel flows or so. This is a different kind of flow structure. Then you have these very persistent trajectories, which are shown in pink here. And it's a mixture of these two which gives rise to anomalous diffusion. And we were able to actually link Eulerian flow features to this Lagrangian anomalies. We were able to say that when you are in the streak region, you are more likely to propel further. And when you hit a spotted region, then you become diffusive. So we've done all of these calculations. If you're interested, I'll refer you to this paper. And that brings me to the end of my talk. I just want to end by saying that we observe this sort of a phase transition in active turbulence beyond a critical activity, where your dynamics goes from being non-universal to universality. And this universality is very interesting because it is intermittent. It gives this maximal chaos and also a host of Lagrangian anomalies. There are also a lot of other interesting things in the system I can talk about, like a scale-dependent flux, finite scaling, and so on. You can read those in the references. And now what we are working on is actually studying this active viscoelastic turbulence. So it's the movie which I showed you in the very beginning. So that was just a clean bacterial system, just very dense. Now what we do is we add a small amount of tracers and particles to it. Sorry, a small amount of polymers to it. And what these polymers do is they change the energetic interactions. They can interact with different length scales of the flow. And we are interested in seeing whether we can control these flows using polymers. So for instance, we are able to tune this anomalous exponent that we saw for diffusion. So this is work in progress. And I want to mention this work was done together with Rahul, Martin, and Samriddhi at ICTS. Here are some references. And I'll be very happy to take your questions. I thank you for your attention. And also feel free to write to me if you want to know more about this work. Thank you.
Thank you, Siddharth, for this very nice talk. So, questions. So, Siddharth, possibly I'll just go and ask a
Yeah.
question. So, what is the typical? I might have missed in between. So, what is the typical Reynolds number in your case that you are simulating for?
Right. So that's a nice question. So typically these flows they occur at very low, vanishingly small Reynolds numbers. So it'll be 10 minus 5 or minus 6. Now the point is that one can construct a Reynolds number here using this gamma naught term that comes in. Sorry, this gamma 2 term that comes in because that's doing the job of diffusion now. And then you can end up with a Reynolds number that's also large, around 1000. So it depends a bit on how you're defining it. Because if you just measure it, I mean, in some way experimentally or so, it has been reported that the Reynolds is very small. But there's been a recent paper by Rahul Pandit's group in ISC where they say, okay, for the highly active case, we can actually call it a higher Reynolds flow around Reynolds of 10,000 or so. So that's possible. Yeah.
So it all depends on what scales you choose, like your characteristic
Exactly.
scales, right?
Exactly. Yeah, exactly.
So in the
Exactly.
classical like scales, if we take, that's the very small. But if you take a
Precisely.
non-classical sort of scaling, then it becomes a higher Reynolds number.
Because yeah, and the issue is the viscosity is a bit strange because you have a fluid that is self-propelling. So it's doing the opposite job of viscosity. So it becomes a little difficult to get the right a proxy for viscosity in the Reynolds number. So yeah, but you can do it through the simulation parameters.
Yeah. Thank you.
Yeah.
Any other question? A quick question, possibly from the audience.
Satya, can I ask a question?
Yeah, please, Francisco, go ahead.
Thank you, Siddhartha, for the very, very interesting presentation. I have a question regarding the last statement you made, like when you want to couple like elastic turbulence or somehow viscoelastic effects with active matters. So do you think that a constitutive model which combines the two is possible? Because I mean the subgrid scales at which we should model things, they don't seem they seem quite to be strongly interacting, and superposition of the two models doesn't seem the way to me. I don't know if it's true.
No, you're absolutely right. So well, firstly, what we will be doing is experimentally. So there we sort of are free from this issue, but then we also want to model the system, of course, and then we want to come up with a constitutive model. So I think the assumption there, so depending upon the choice of polymers, because you can also have very small polymers. So the ones that we are introducing now are, let's say, 1,000 times smaller than the size of individual bacteria. And you already have a coarse grain description for the bacteria. So you're again sort of zooming out. So the polymers will become super subgrid in some sense. So I hope we are able to add some constitutive relation that will reflect what we do in experiments. But yeah, that needs to be seen.
Okay, thanks.
Yeah, yeah.
Thank you,